Oh, hi. I'm Chris Martin. You may remember me from such things as Class or Shrek the Musical. So you want to learn about resistivity? Well, calm down there, buddy. I'm here to help. Let's go. The first thing you're going to want to know about resistivity is that it depends on the material. Typically, the lower the resistance, the better the wire is. The most ideal wire has no resistance, but that doesn't exist in the real world. From the resistivity equation, the lower the resistivity, the lower the resistance, and the better the wire. Resistivity is also dependent on the temperature. So the more wires heat up, which happens as current runs through them, the more resistance they take on. It's one of the reasons why your cell phone starts to behave a little bit worse when it gets really hot. The amount the temperature affects the resistivity depends on its temperature coefficient. This temperature coefficient is measured in inverse degrees Celsius and can be found on the chart right here. Alright, let's say you got a wire. Now to make this easier to visualize, I got us a cylinder right here. This is one big honkin' wire. To find the cross-sectional area, imagine that you slice the wire, cut the cylinder at a 90-degree angle, and then turn and stare at it dead on. What you see is just a circle. So the cross-sectional area of a cylinder, which is the shape of most wires, is going to be a circle. So make sure you understand how to find the area of a circle in order to do these problems. So a quick example of that. I like to flaunt my vast amounts of wealth, so I only use pure gold wire for the electricity throughout my entire house. So if the wire heats up to 140 degrees Celsius, what is its resistivity? Well, to answer this, I'm going to have to go look at my chart real fast. And from the first chart, I will find the resistivity at 20 degrees of gold is 2.44 times 10 to the negative 8 ohm meters. And the temperature coefficient of gold is 3.4 times 10 to the negative third, inverse degrees Celsius. So to find the new resistivity, I would just use rho equals rho naught times 1 plus alpha times delta T. Since my new temperature is 140 degrees Celsius, delta T, that's the change from 20 degrees, that's just going to be 120 for delta T. So, plugging in that 120 for delta T, times 3.4 times 10 to the negative 3 for alpha, add that to 1 and multiply the whole thing by 2.44 times 10 to the negative 8 ohm meters, I should find a new resistivity of 3.44 times 10 to the negative 8 ohm meters. Well, now that I know my resistivity, I can use this to figure out something more useful, like the resistance I'm going to get in these wires. So let's say it has a length of 50 meters and a diameter of 0.723 millimeters, less than a millimeter. What is its resistance? Well, this one's going to be pretty much a simple plug and chug into my resistance equation. The area of a circle is pi r squared, and now I just need to plug in my values. Be very certain that you're converting back to base units for everything, like many of the physics problems this year. Additionally, when solving for the radius, look very carefully at what values you're given. In this case, I was told the diameter was 0.723 millimeters. So I got to convert that to meters and then divide by 2 to get the radius. And this is the value that I'll plug in for r. So got all my values for all my variables, now I just plug and chug. And I end up with a resistance of 4.19 ohms. So it's not a whole lot, but it may be enough to be significant depending on the other resistances I'm dealing with. Thanks for watching. Now that you've seen how to work this problem, you should be able to tackle some on your own. But for now, leave me alone.